So today I'm pretty happy to be presenting Shackle. It's something I've been working on for the last year. And basically, like he said, I work at a company called Gauthier, and our main product is a real-time bidding platform. And for those who don't know what that is, basically it's to buy ads in real time on the web. And the fact that it's real time, there's time constraints, so performance is very important, and the load is massive. So we have hundreds of thousands of requests a second. So performance is crucial for us. So the problem here we're trying to solve, building clients, is basically a client to talk to a server. So we have an application, we want to talk to a service. How can we make this as efficient as possible? A service for Shackle, basically it's something that communicates over socket. It can be a text protocol or binary, and then it can be a synchronous or asynchronous protocol. And so for example, it could be Cassandra, Memcached, Kafka, HTTP2. The goals when I started this project, I had 4 goals. So the first one, reusability. So at Gauthier, I've been maintaining 6 or 7 different clients for different services that we talk to. And whenever we'd find a performance bug or regression in one, then we had to fix all the other ones. So it became really complicated to deal with that. So my first goal really was to rip out all the reusable parts and build a framework with that. The 2 other points, speed and concurrency. Speed, obviously, is kind of the time the request takes. Concurrency is how many requests you can do at the same time. And then finally, safety. In our system, we try to not let it crash just because usually that code path is slower than the normal code path. You might be logging, you might be generating stack traces, and if that happens when you're answering like 20,000 requests a second and you're crashing 20,000 times a second, that affects performance quite a bit. The other part of safety is more on the protection of the VM itself. Since the queues are unbounded, we need some sort of back pressure so that we don't run out of memory. So if the service slows down or there's an issue with the service, we don't want to affect the rest of the system. So I'm going to go through kind of the design process, starting from the most naive implementation to the current implementation. So really the most basic thing you could do is just in your process, when you want to do a call to a service, open a socket, send your request, receive, and then close the socket, and that's it. That works. If you have to do like 5 requests a second, that's fine. But obviously there's problems. A lot of overhead doing the connection or opening the socket. There's also can be setup overhead if, for example, your protocol needs to be initialized or you want to set default values. And there's no connection limit, so you can run out of FDs and of memory. So design 2. I guess this is kind of the basic Erlang 101. So instead of keeping your socket in your process, well, you have a server, a gen server, that keeps that socket in the state, and therefore you don't have to reconnect and open every time. This works, but then how do you find your server? So if you only have one connection, it's fine. You can just use a register name. If you have multiple connections, then you either need to know how to generate those names, or you need to keep a list of all the PIDs available. So the naive approach to this is to introduce another gen server, which is a pool manager. And this pool manager will track all the servers for you. Now, the problem with this approach is now you're sending 2 messages per request. And if your pool manager is slow, you're adding latency. And also, the pool manager is basically a single point of contention. If it blocks or anything, all your requests will be affected. So how can we solve this? One solution is that instead of using a pool manager, we just store a little bit of information in ETS, and from that information, we generate the names of the servers. So for instance, if I had a pool that's called Marina, and I know there's 4 servers in the pool, I can know that if I always use the same structure, that there's 4 servers, Marina 1, Marina 2, Marina 3, and I can auto-generate those names and just send the messages directly to those gen servers. Okay, so we've solved kind of the finding the server. Now we need to improve on concurrency. So I didn't show the code for the gen server, but the naive approach in gen server would be that basically you get handle call, you send the request, receive the request, and reply directly. The problem with that is obviously it's not really concurrent because it can only handle 1 request at a time. So a trick you can do is actually not reply in the handle call. So you send the request, enqueue who did the call in a queue that you keep in the state of the gen server, and when you receive the data, if you're in active mode, you can queue out who did the initial call and just send the response directly. So now we're not blocking on actually receiving the response, and we can do multiple requests per gen server at the same time. So now this is our new design. Now it's concurrent. So if we have, well, we can do as many requests as we want, but do we have safety? And in this case, no, because now since everything is async, we have no guarantees of any kind of back pressure. So if the server slows down, if anything happens in the system, it's possible that you'll just enqueue a million messages, run out of memory, and the VM dies. So the solution to this is to use an ETS table, which we use to build a backlog. So whenever we want to send a message to a server, instead of just sending it directly, we ask the ETS table by incrementing a counter, and we make sure that we're not over the limit. If we are over the limit, then we fail fast, and we just decide to reply that we're too busy right now. Okay, so we fixed that problem. Now, it's fairly safe, but we can do better for speed. Gen server is great, but there's a lot of functionalities that we're not using, so we can actually just switch to using proclib directly, and we're going to be a little bit closer to the metal. And the queue implementation from the standard lib is okay, but switching it to like an ETS table is faster and also permits to do out-of-order async protocols. So the new design, now that we have, so whenever you're sending a message, you call ETS, check if the backlog is not full, and then if it's not full, you send the message will go to service, comes back, and back to our process. And it's as efficient as we want, and so we've attained basically our 4 goals. From there, I'm going to talk a little bit of the architecture of Shackle. Shackle is fairly simple, so there's 4 core modules: Shackle Pool, Shackle Backlog, Server, and Queue. So the Shackle Pool supports 2 different strategies for picking the clients, random or round robin. Round robin is the default. And again, it leverages ETS, so there's no manager. And there's no ETS contention since we're always just doing reads to that table. And the pool itself is very low overhead. It's almost constant time. Shackle backlog. So the backlog protects from out-of-memory errors. Leverages ETS again, no manager. The way it's implemented, it's always 1 backlog per server. and it uses ETS update counter, which is super fast and atomic, and that has a special property that when we do the increment, we actually get the value back. So if we set the table to write concurrency true, we're actually always just doing write, so we never block, and we get the read for free. So this is kind of to show how the backlog is implemented. So we're using a trick here. Basically, we're doing the update ops at the bottom, and we're doing two operations. The first one, we're incrementing the counter by 0, and then incrementing the counter by 1. But we limit the max value can only be as large as the backlog size. And when we reach that value, we set it to the backlog size. So what this does is basically when we do the increment, if both values are the same, it means that we weren't able to increment and that we reach the backlog limit. If the two values are different, then we were able to increment, and we can actually send a message to our server. So Shackle server basically uses proclib. If you're not familiar, proclib is kind of the behavior gen server implements, and all the gen event and all of that. It gives you some nice things like tracing of the state and supervision. Also, the Shackle server, basically, it's been optimized so that everything in the hot loop is asynchronous. Nothing should block ever. It should be as fast as possible. It uses binary matching as much as possible. It uses IO list as much as possible. If you can skip creating binaries, you should. And then it's skinny in the sense that all the extra work that we can do outside of the server is then outside of the server, so that, again, the hot code path is as efficient as possible. Shackle Q, like I said earlier, it's using an ETS table, faster than the STLib Q module. And the nice thing of using ETS is that the normal queue is in order. If we get messages out of order from the service, we're screwed. So this actually permits us to build clients for more asynchronous protocols like Cassandra. And again, there's no contention since there's always one producer and one consumer, and it's always the same server. So since it's that one server, it's never fighting with anyone else to get access for the locks on the keys. Now we're going to go over an example of actually building a client. So to build a client, what you have to do is you need to implement the Shackle client behavior. The behavior is fairly simple. There's an init, a setup, handle requests, handle data, and terminate. And that's kind of what the life cycle of a client looks like. When the client starts, it calls init. Init will initiate the state of the client. After that, once the socket is created, you'll receive the socket in, actually that's wrong, but you'll receive the socket in setup. And in setup, you can set up your client. So let's say you're using Cassandra, you want to set up the default key space, that's where you would do it. And finally, we get to the good part. So if a client wants to do a request, you'll receive and handle requests. This is where you're going to serialize your Erlang term to your protocol. When you receive the answer back, you'll receive the data and handle data. This is where you decode the data to the Erlang term to send back as a response to the process. And finally, when the client terminates, if you're closing the pool, you can clean up your state. So the example we're going to use today is a simple arithmetic service. So this service works over TCP port 8080. And there's a session setup, and it supports two operations, so addition and multiplication. And so the setup is really simple. You send text init and caps, and you receive response OK. And then for the operations are binary. So request ID, which is a tiny int, an operator, and 2 operands. And then the response is just the request ID and the results of the operation. So we're going to go over the 5 different callbacks for this particular case. So in it, so like I said here, it's to initiate or initialize the state. In this case, our state, we don't need to do much because there's default values. But so we have a buffer, which is an empty binary when we start, and a request counter that starts at 0. And so if we do the setup, so setup, you receive the socket and the state. And when you receive the socket, it's set to active false, so you can do synchronous send receive. So in this case, what we do, we send init. If it succeeds, then we do a receive. We're expecting OK. If we don't receive OK, well, in this case, it's going to crash. But in theory, yeah, that's not really good. But it's a toy client. So you receive OK. And if there's any kind of failure, you can return error reason. And it's going to shut down the client and try to reconnect with incremental backoff. Handle requests. So handle requests, it receives the actual Erlang term for the request and the state. So in this case, it's a tuple of operation and the 2 operands. And we pattern match out the request counter because we need the request counter to generate a request ID. And so the request ID, I'll go over those 2 methods in the next slides, but basically we have a request ID and we generate the data, and then what we return is OK, the request ID, the data, and the updated state. In this case, what we use for the request ID is just a modulo of the max that we can assign for the protocol. One thing that you have to note is that the request ID needs to be unique for all requests inside the same client. So in this case, the protocol only allows up to 255. And therefore, when we set up the backlog, the maximum request we can set for that server is only 255. If we set it to like 1,000, it's possible that we'll reuse the same ID, and we're going to be confused in the queue. It's going to overwrite the queue. So protocol encoding, for this is fairly easy. So we have 2 operations, add, multiply. Add is using 1, multiply 2. And then the request ID would just generate the binary. So request ID, the opcode, and the 2 operands. And so that was it just to do the request. We're like halfway done already to build our client. Handle data, you receive the data back and the state. And the expected is that you send back OK and your response and the updated state. So when we get the data, we pattern match also the buffer from the state. It's possible that you'll receive data that was too large for a TCP packet, so it'll be over multiple packets. So you want to keep a buffer in your state so that you don't corrupt your data. And then we call parse replies, which is this method. Again, since the protocol is so trivial, all we have to do is loop around with a pattern match. When it stops matching, whatever is remaining is basically your new buffer. And in this case, so we return the response is the request ID and A, which is the response of the operation. And a response is always a tuple of the request ID that you assign and the response you want to send back to the caller. And finally, terminate. If you have any kind of, I don't know, a timer or something in your state that you need to clean up, cleanup, then you can clean it up at this point. So we've implemented the module that is our client and implements the behavior. How do we actually start a pool? So what you need to do is just call Shackle pool start. You need to assign it a name, which is an atom, and then your client, which is the module that implements this behavior. And then there's two lists of options you can send. The first one is the client options. So the client options, these are the client options available. So the IP or host name where you want to connect, the port, the protocol. Protocol, we support TCP and UDP. And then there's a Boolean for reconnection. So do you want to reconnect on failure? And if you do, then there's a minimum and a maximum time to do the exponential backoff. And finally, the socket option. So if you're using a text protocol, you can not use binary. If you're using binary, then you can do any kind of tricks or optimization there for your own protocol. And the last list of options for the start is the actual pool options. Currently, what we support is the backlog size. So it can be a positive integer or infinity. Infinity was added, in theory, it's kind of against the safetiness of this. But if you're using a UDP, it's possible that you're going to lose packets over the network. And you're just going to end up with backlogs full that never empty out. That way, if you use infinity and use kind of the asynchronous mode, you won't be just blocking forever in busy mode. And then the pool size and pool strategy. Pool strategy, like I said earlier, support two modes, random and round robin. So if we do run this command, so the start, what we see is that the setup was called. We sent init, we received OK. And then now we actually want to do the fun part. We want to actually do an addition or a multiplication. So all you have to do is called Shackle call, the pool name, and the actual operation you want to do. So in this case, it's just add in the two operand. And it's the same thing for multiplication. So if we do run the client, we do add. So you can see this was the first request of the client. So the first byte is 0 because the request ID is 0. Second byte is 1 because the operation is an addition. And then the two operands 5 and 10. And you get the response with the same request ID 0, and then the response of 15. And then again, same thing here for the multiplication. Now we're request ID 1. And the operation is 2, and then it's 2 plus 6, or 2 times 6, and then the request ID 1, and we get the 12. If you want to do async, instead of calling Shackle call, you can do Shackle cast, and it will remove the whole receive loop that call usually has. So some tips and tricks. So if you're building your own client, you should pattern match as much as possible. It's efficient, and also I think it's easier to read than big cases and cases. So for maintainability and performance reason, I suggest you use pattern match as much as possible. Using IO list as much as possible. If you don't need to create a binary, you'll save allocations. So as much as possible, try to be lazy and not create binaries. Another point is to keep your client lean. And by that, I mean in those callbacks, if you can do the work outside of them, try to do it. So for instance, some protocols, they'll send you the size first. So you don't need to decode the whole packet. Once you know you have the whole packet, you can send it back to the client, and the client does the decoding itself. And that way, your server will be able to handle more requests per second. And if you need share state, use an ETS table. So for instance, if you need a cache of some sort, suggest ETS. And then again, measure, measure, measure. I've talked about this in previous talks, but it's really important to measure whenever you make a change. If you want to be careful about performance, it's impossible to just kind of guess what the outcome of a change will be unless you measure. So for Shackle and all the clients I've built, I've started implementing a make target, which is a make profile. It uses fprof_x, which is kind of a fprof clone, but that you can remove the sleep time, and it does the conversion to a format that you can read and cache grind. If your OS doesn't support cache grind, there's alternative. There's Q grind and K grind, or K cache grind and Q cache grind. So this is kind of the output. When I run make profile, this is what I get. So I can get time for the whole application or per module. It's very useful, but you have to be careful and also measure actual time. Since the profiling, if you were at Lucas' talk yesterday, the Erlang profiler actually has the Erlang tracer has a global lock, so that every event has to go in the same queue. So one thing I've noticed is that if you force inlining in your module, then you have less function calls, and then everything looks like it's magically faster, but it's just less contention on the lock. In 19, it should be better, but currently you need to take the numbers with a bit of grain de sel. A grain of salt. Yeah, is that an expression in English too? Yeah, all right. Yeah, but this has been really useful. I've found some performance issues between versions 0.1 and 0.2 that have improved. One thing I did was in the 0.1 version, there was an extra callback called handle timing. Handle timing gave me information about the timing of the request, and actually it turns out after profiling that half the time of my requests were spent doing the timing stuff. So really, the overhead was way too big. It also made me realize that my random strategy was slower than round robin. Round robin uses an ETS counter that just updates the counter and wraps around. The random was using phash2 and the PID plus a timestamp, and just doing that was kind of slow compared to incrementing a counter. So I switched to that. There's also, I have a fork with a NIF to do the random, which is actually faster than this, but it's not merged yet. Maybe I'll merge it, but I'm not convinced I want to introduce NIFs in this. And finally, after profiling, I found out that the actual generation of the atoms of the name of the servers was slow. I've tried finding hacks around it, but I couldn't find anything. So now there's the Shackle compiler in the project that basically when you start a pool, it uses the information of all the pools in ETS, generates a module, and so it's just I call the pool name the index of the server I want, and it just returns me the atom that was compiled in the module. So to give an idea of a little bit of performance, this is a graph for 1 day of memcache call. During the day, it gets busier, so performance degrades a little bit, but you can see that during the night, it's about 200 microseconds. And this includes network time, which is about 120 microseconds. So it gives you an idea how tuned this is to do the actual memcache request. And then usage. Currently, there's 2 clients that are open source and fully functional used in production at Adgear. So there's Anchor, which is a Memcached client, and there's Marina, which is a Cassandra 2.1 client. And I'm working on 2 other clients that are also going to be open source. Boy, which is a HTTP 1.1 client, and Flare, which is a Kafka producer client. For the Kafka producer, the plan is to do kind of best effort at first, and then work on more of the safety of not losing messages. But again, for our use case of sending hundreds of thousands of messages per second, that's kind of what I'm going for first. And then, so this is a graph of the requests we're doing per second using Shackle right now at Adgear. So peak, we go around about 1.3 million requests per second, and we envision this growing quite a bit in the next few months. Finally, the future for Shackle. Currently, there's no kind of support for if you want to you talk to multi-node. So you can start multiple pools, but to load balance between those pools, you need to implement it yourself. That works, but there's optimization you can do if you do it at the same time you start the pools, so that you don't have to check twice which pool, or twice the decision of which pool to take and then which client to take. You can do it in one step. And then I want to improve test coverage. It's not that bad, but it could be better. And I've started playing with property-based tests for it. And hopefully I can get it fully tested and be confident for the future when I make changes. So these are the links to all the projects I've talked about. Basically, just go to my GitHub. Everything is there. And yeah, that's it. Thank you.
Can you bring back the previous slide?
Yeah, for sure. Is there any questions?
We have like 10 minutes for questions, so go ahead.
Yeah, I talked a little bit fast. Yeah.
Did you find that there was any overhead with passing IO lists from one process to another? Considering you have to garbage collect and throw the heap on the receiving process, and if you consider instead possibly passing the, say, open port out to the process that's generating the IO lists, so they can do essentially a single copy?
Repeat? Yeah. So the question is basically, have you thought of, instead of passing around IO lists, just passing the socket so that you don't pass the IO lists and cause copy? Currently, most of the IO lists are always generated in the server, since it's like it would be most of the IO lists are generated in the handle request, and usually I do that work in the server itself, so it's not that bad. But no, I haven't tried optimizing for copy yet.
Can you cover it again? What's the advantage of the prop list over just using a Gen server?
So the advantage is basically, so the question is, what are the advantages of using proclib instead of Gen server? So it depends on your use case. If you're just doing a couple operations per second, it doesn't matter. But for us, like every cycle is kind of important. So the Gen server implements a lot of different features that are all in the hot code path. So when you're doing a call, I don't know if you've looked at the code, but there's a lot of different code paths, a lot of complexity that we don't need in our case, since we're kind of re-implementing that logic in the pool. So for us, it just makes more sense to go to something simpler, and it's just a little bit more efficient in terms of number of cycles spent doing this.
So how much are you saving?
I haven't actually measured. Well, I have in the past, but I don't remember exactly the numbers. It's probably not that much, but I like to over-optimize my stuff. Yes?
Question. Can you elaborate a bit more on the naming and resolving the naming to hidden? And would the actual naming be built into the bottleneck at some point because you're resolving this all the time?
Yeah, so the question is, can you elaborate on how the naming is done for the servers? So basically, the problem, we can look at some code. The problem is that you cannot, to register a name of a server, it needs to be an atom. And because of that, when the information I have from the pool is just the base name and the index of the server I want to talk to. So to generate the actual atom, I have to do the base name plus integer to list, and then this list to atom. And just doing that operation is fairly costly. And so the hack-ish I've done is that if we look at the compiler a little bit, basically I auto-generate a module that's called Shackle pool util, and it exports one method called server name. And this server name, the clauses, it's always the pool name, or here, the pool name, and then the index. And then the return is the actual server name. And the server name is server atom. And as you can see here, this is the costly operation that I wanted to optimize out. So instead of doing this every time there's a request, now I compile this into a module, and I can call it, and I don't have to redo this operation. Does that answer your question?
So partially.
Partially, okay.
My question was also about when you actually ask the VM, here's the atom, and I want to pit that.
Mm-hmm.
So is that sort of operation would become a bottleneck to do millions of them per second?
So I register the name to the server. So I never do kind of where is the server. I just send it directly, and it uses the global or the process registry in the VM.
Yeah, that's what I'm asking about.
But there's no solutions around it, so I haven't thought about it, to be honest. But maybe Benoit, did you have that?
About you may not be obliged to have that hack.
Okay.
Using the atom to exist. You have an atom to exist.
Yeah, but it's the same.
To exist in atom, so you do a try and catch. And then
But it's not faster.
No, but you don't have all that code in your code.
No, but it's not still, whenever you convert, it's the converting the list to atom that's expensive.
Yes, but once it's done, you just have to check if it exists.
Yeah, but the code checking the existence is the same code as creating. Like if you do list to atom or list to existing atom, it's exactly the same code path. It's just if it doesn't exist, it exits. I've looked at the code. Yeah. But to finish answering your question, that doesn't come out in profiling. I would need to profile more with system tap or something that I can get introspection in the VM itself.
Yeah, because it seems like with that system, it becomes a single detention point. The question is how it's implemented.
Mm-hmm. From my experience, that part is fairly scalable, and that's kind of partly why I think it's fast, in part because it only accepts atoms instead of having a tuple, but it breaks other parts in the VM. I've looked into maybe patching the VM, but it's not something that can be done easily.
In your production system, what sort of pool sizes are you using?
The pool sizes are actually fairly small since you can do a lot of operations concurrently. So I'd say the memcache doing, per server doing maybe 20,000 requests a second probably has 8 client with a limit of 248 backlog, and that's enough to handle. Since the requests are so fast, it doesn't really matter. Yeah.
Would you align in
Well, if your application is only doing kind of that, then I guess, well, no, I don't think it, actually, you'd have to benchmark that, but I don't do that. The scheduler, the Erlang scheduler is really good, so you don't need to kind of do that. And especially you can't pin down processes to a scheduler, so at the end of the day, they're still going to travel around on different schedulers, so I don't think it would make much of a difference.
I was just going to ask if you put any thought into having like a maximum lifetime for connection, so the connection cycle on some regular interval?
Yeah, so currently no, because we want to keep the connection as long as possible, but right now I'm writing an HTTP client, which in normal use case, you might not want to keep it always open. So yeah, that will be coming soon.
Okay, thank you very much.
All right, thank you, everyone.